Hi everyone, this is Manas, your friend and tutor, and for today's session you've got to be curious and you've got to be able to explore all the options available to solve a particular problem, to approach a particular problem. Let me tell you why. Pause the video and just take a closer look at this. So what you have is a portion of the beam, and more so you have the cross section. The cross section is a 60 by 120 cross section. You know, this green line, this dash dot line over here is the neutral axis, and its location is known to us. From the topmost fiber it is 60. You can also say from the bottommost fiber it is 60. It's perfect, no problem. What we need to work out is the value of the internal moment at this cross section, and obviously that internal moment would be acting like this. You've got the thumb in the direction of neutral axis like this, internal moment. This internal moment has to be found using the Flexure formula, and it's very easy. You just need to plug in all the values and you'll be getting the internal moment. But the fascinating aspect of this particular problem is, just try to read this. You need to find the internal moment by finding the resultant of stress distribution using basic principles. And even here you've got to explore two options, using the calculus approach and then using the basic math approach, using the common sense approach, you can say so. So there are going to be three different approaches to this particular problem for calculating the internal bending moment, which in fact is acting about this neutral axis in this way. See this, all the forces this way, all the forces this way. So everything above the neutral axis, all the points, if I mark all the points above the neutral axis, all of that is undergoing compression. That's why the direction of arrow. And all the points, if I mark them below the neutral axis, will be undergoing tension. Right? That is why the arrow is outwards. Okay, let's jump right into it. Here we go. Okay, let's start the solution. It's going to be wonderful. What do we want? We want the Flexure formula. Okay, by the help of that Flexure formula, we'll be working out the internal moment. Beautiful. So let me just write the Flexure formula, and we already know that at a distance of 60 millimeters, we have this maximum bending stress, that is 20 megapascals. You can also say this, guys, this is going to be equal to 20 Newton per mm square. Just try to do the conversion. I'm sure you can get there, right? So sigma max is equal to mc over I. It's not just any I with respect to the neutral axis, and the c is the distance farthest fiber. Let me write it, put it up this way, distance of the farthest fiber, and you can clearly see this is the farthest fiber. Okay, actually the fibers are here in this fashion, and like this, the fibers are here at a height of how much? At a height of 60 millimeters. So that is going to be equal to 60 millimeters. You can also say that this is going to be equal to 0.06 meters. Okay, let us approach this problem in SI units. Let us do Newton, meter, all of that. Okay, so that was all about value of C. You know what is sigma max? That is 20 megapascal. That is known to us. No problem. What is supposed to be calculated is this fellow over here. That is the internal moment. Because of this stress distribution, it is quite obvious. Now guys, this is lecture number 3 of bending of beams. If you are straight away watching this video without watching lecture 1 and 2, well then do leave right now and straight away go and watch my lecture number 1, where I had derived everything regarding the Flexure formula. All the parameters were explained, right? So do watch that video, and once you watch that video, all your concepts regarding beam bending will be absolutely clear, and you will be able to perceive the problems in a better fashion, and your approach will also enhance. Okay, so this is known to us. How much is this value? We know this very well. This is 20 MPa. Okay, we need to work this out. I neutral axis. Just take a look at this. Let me make this B, and that's D. Its centroid is going to be right here. Okay, so let's say this is XX. Okay, this XX is the centroidal x. How much is this? BD cube over 12, isn't it? We know this very well. And in this case, this centroidal is also its neutral axis. So obviously this is going to qualify. You just need to calculate that value. I neutral axis is in fact I centroidal axis, which in fact is BD cube over 12, and you just need to plug in the value. How much is B? That is 60 millimeters. Just put this value in meters, 0.06 into d cube. How much is d? 60 plus 60, that is 120. So that is going to be 0.12 and its cube. All of that divided by 12. You just need to plug in the values in a calculator, and let me just write how much that has worked out. I've got the entire solution with me. Here it is. So 8.64 into 10 raised to minus 6. All right, 8.64 into 10 raised to minus 6. Where can I write it? 8.64 into 10 raised to minus 6, and the unit, obviously area moment of inertia, that is meter raised to 4. You just need to plug in all the values. Let me show you, and then obviously you can find this internal moment. Okay, how much is sigma max? 20 megapascal. That means 20 into 10 raised to 6. Now this is in SI units, Newton per meter square. Equal to M has to be calculated, so let me just keep it, write it as M multiplied by C. C is 60 millimeters, so in meters it is going to be 0.06 divided by obviously the area moment of inertia, 8.64 into 10 raised to minus 6 meter raised to 4. Let me just quickly do a check. 8.64 10 raised to minus 6. Fine, perfect. So the value of internal moment, let me tell you, the value of internal bending moment which you are going to get is equal to 2880 Newton meter. You can also write this as 2.88 kilo Newton meter. Perfectly right. No issues. It's absolutely perfect. Right? Alright. Now let's proceed. So this was our first exploration using the Flexure formula. We know everything about the Flexure formula and we just wrote it. This is one version of the Flexure formula. Let me tell you, if I don't know whether you guys remember this or not, Flexure formula can be written in two ways. One, in the form of maximum bending stress. This is equal to sigma max is equal to, this is exactly what I wrote, MC over I. MC over I. One more way of writing the Flexure formula is this way. Sigma is a function of phi, right? Just try to listen to this once again. Let us recapitulate. Sigma is a function of y is equal to negative of my over I. I always call this equation as a selfish equation. Why? My I, that's why. So all positive values of y are going to fetch negative values of sigma. That means for all positive values of y, if you go upstairs with respect to this neutral axis, if you go upstairs, positive values of y, but obviously the nature of stress is going to be compressive. You can see this. Everything above the neutral axis is undergoing compression. And for all the negative values of pi, that means if you go downstairs, you will have corresponding positive value of stress. See this outwards. That is why. Anyway, so these are the two different versions of the Flexure formula, and you can use it as per your choice and as per your requirements. Anyway, let us begin now. Another approach. This is going to be very fascinating, and I don't know if you have ever come across this or not. Let's approach this. Here we go. So this was basically approach one, right? Second approach. Let's make some space. Guys, watch. And this approach is basically using calculus, via calculus. So a lot of drawing needs to be done before applying the method. Let me just show that to you. You'll eventually understand everything. Just take a look. What do we want? We want the internal moment, isn't it? And one more thing. In lecture number 1, I told you that the net force on this cross section, or even on any cross section, net force on any cross section is going to be equal to 0, right? And we'll prove it here. And we'll also find the bending moment, which again will work out as 2880 Newton meter. You will see that very soon. Okay, just take a look at this. That's the beam. Let me make the beam smaller figure, right? Manageable, and then this. Okay. Now somewhere here, what we have is the neutral axis. Done. Right? What we'll try to do is, guys, just take a look. Now let me have the black pen, and somewhere here, Just take a look. Pretty bad. At a height y, I've taken this small element, very small element, right? This is dy, and because of that there is going to be some corresponding area. That area is going to be dA, and let us call this dA is equal to, just watch, how much is this distance? 60. So dA can be written as 60 times of dy. Once again, what we have done with respect to the neutral axis, this is the neutral axis, okay, and at a distance of y, I have taken a very small aerial element, you can say, right? This is having a height of, this small element is having a height of, or width of, or thickness of dy, you can say. So that dy multiplied by this distance, which is equal to 60 millimeters, will give you the area of this very small element. What exactly we'll try to do? Let me demonstrate. So a very small force will be acting in this element, isn't it? Let's call this force as dF. Just listen to this very carefully. This is going to be very, very interesting. What my aim right now is to prove that the summation of all the forces acting on this cross section because of this stress distribution is going to be equal to 0, and that is going to be proven. F net is going to be equal to 0. So from here on, guys, we've got two wishes. One is to prove that the total force acting on this cross section because of this entire stress distribution is equal to 0. That is our first wish. And secondly, we also need to find the internal moment. Both the wishes are going to be accomplished. Just keep watching, and let me just write this. Total force F net is going to be equal to 0. We wish to prove this. How? Let me tell you. Okay, just take a look at this. This is a very small area, that is dA. dA is equal to 60 into dy. It's quite obvious. We wish to find the total force acting on this area. How? Again, force is the product of stress and area, isn't it? Force is the product of stress and area. Okay, so this stress is not just any stress. This is not a fixed value. This is rather a function of y multiplied by, this is not just any force, this is dF, this is going to be dA. So this dF is equal to sigma as a function of y times of dA. What I wish to accomplish now is the value of sigma y. You need to note this. Sigma y can also be written as minus y by c times of sigma max. Now some of you guys might be wondering, from where the hell has this equation come forward? Well, this has been taught in lecture number 1. If you still haven't seen my video, Bending of Beam lecture 1, go ahead and watch it. Link to which can be seen in the description. Anyway, just take a look. Minus y, what is c? The maximum value, farthest distance, okay, that is 60. 60 multiplied by how much is sigma max? Well, that value here we have put it up in millimeters, so this sigma max also I'm going to put it up in millimeter square, that is 20, right? This is 20. So if you try to work it out, this is going to be minus y by 3, and again this is Newton per mm square. Let me clarify this. So I'm going to write it over here. Sigma at a distance y from the neutral axis will be equal to minus y by 3, and let me clarify, the unit is obviously Newton per mm square. It's getting a bit lighter. Let me use this. Alright, so that was all about sigma y. Okay, now just take a look at this. You just need to frame this formula. For finding the total force, you need to integrate the force on a very small area. Listen to this very carefully. For finding the total force on this entire cross section, first of all try to focus on this very small elemental area. If you can find the total force on this very small elemental area, then you can integrate obviously from this point to this point to get the total force on the cross section, which eventually will work out as 0. Okay, just watch. Total force, it's not 0, let's say. What you can do is work on a very small area, that is dF. How much is dF equal to? dF is equal to stress, that is as a function of y multiplied by area. Okay, stress as a function of y. You need to integrate this for finding the total force or the net force on this cross section. Like how much, what is the value of sigma y that you are going to plug in? That is minus y by 3. Do note it, do note it. I have to rub it off after some time. So that is going to be equal to, with a negative sign, integration minus y by 3, what else? Times of what is dA? So guys, just watch. dA is nothing but 60 dy. Let me plug it in. 60 dot dy, and there you go. Obviously, with respect to the neutral axis, we have taken this distance, and if you are going to the top, if you are moving from 0 to plus 60 and this is from 0 to minus 60, so basically what we'll try to do is we'll try to slide this from minus 60 to plus 60. So all the area will be covered. That is the best way forward. So minus 60 to plus 60, this is the best way forward, and you just need to solve this equation. I would suggest you guys to note this down. That is very important, how we've reached this. Pause the video and note it down. Okay, here we go. What do we have? Minus y by 3. So 3 times of 20. Okay, 3 times of 20. Here we go. So this is going to be 20, and then there is an integral minus 60 to plus 60, and then you've got y dot dy. Obviously this is going to be equal to 20. Y dy we know very well, y square over 2, and this is going to be minus 60, this is going to be plus 60, and this is 210. This is very elementary. This is going to be y square, that is 60 square, minus of 60 and its square. Obviously this is 3600, this is 3600. Okay, minus, obviously the answer will work out as 0. So this is something which we have already seen in the derivation also. F net is going to be equal to 0. The net force on this cross section is 0, but not the net moment. The net moment will have a non-zero value, and I'll show it to you here. Okay, so that was all about the forces. Now we need to see what is the net internal moment because of this arrangement of force. Right here it is tensile, not tensile but compressive. Here it is tensile. How can we do that? It's going to be very easy. Just focus on a very small moment. Focus on a very small moment. There is this force at a height of y. From the neutral axis, the moment is going to be, if you watch, you can just draw a line over here. This is 90 degree. Okay, so force multiplied by this perpendicular distance will give you the value of moment. If you watch again, the thumb is pointing this way into the board. That is a positive moment. Okay, that is a positive moment. We'll do the integration, right? Because of this very small force, there is going to be some very small moment, and if you want to find the total moment, you have to take all the forces out into consideration, and for that you need to integrate. Let me tell you exactly what I'm trying to say. This force dF at a distance of y is creating a very small moment, that is dm. Quite true, right? We'll plug in the limits later on, don't worry. This is going to be dF multiplied by simply y. Okay, that is dF multiplied by y, and obviously the limits are going to be from minus 60 to 60. That is no big deal. Equal to, what is dF? dF is nothing but sigma as a function of y multiplied by dA, and then just write this y. Okay, we'll plug in the limits later on. Just keep watching. Here we go. Now what? If you watch sigma y, we already know sigma y is equal to y by 3. You forget about the plus minus sign from here, right? We already know, since it is inwards, the thumb is into the board, this way the moment has got to be positive. Okay, just forget about the sign, just simply put it up. That's the integral sigma y, write it as y by 3. Y by 3 multiplied by, what is dA? dA 60 dy multiplied by 60 dy. Beautiful. What's next? That is done. That is done. What is left? Y. Again, this is going to be super awesome. So this is now become y square, and this 3 times of 20 is 60. Now 3 times of 20. Now we have the integral inside, that is y square dy, and that is from minus 60 to plus 60. Right? Just try to solve it. Just try to solve it. This is going to work out as 20. Inside the integral, y square will become y cube by 3 from minus 60 to plus 60. Again, just let me plug in the values. This is going to be 20 over 3 20 over 3. 6 is 36. 36 into 6 is 216. So 216. 216. How many zeros? 1, 2, 3 zeros. Minus. Again, this is minus 60 and its cube. Had it been a square, then minus would have vanished. Since it is a cube, an odd number, therefore the negative sign will remain. And that negative sign will remain. What we have is 216, 1, 2, 3 zeros, and that's it. This is exactly what you get. You just need to solve this. So that's 288,000. 288, 1, 2, 3, 4. Not 000, it's quadruple zero if I'm not wrong. 288, quadruple zero. And obviously, guys, from here we started. We took sigma y. Sigma is a function of y in Newton per millimeter square. All the values that I have plugged in, the 60 also, everything that I have plugged in, everything is in millimeters and newtons. And therefore, since it is the bending moment, force and distance, Newton and meter, it's not going to be meter over here. It is going to be rather Newton millimeter. Well, obviously, you can do the conversion. Well, millimeter, milli is nothing but 10 raised to minus 3. You strike this 10 raised to minus 3 with this figure over here. So 3 zeros will cancel out. What you have is 2880 Newton meter. If you are still not satisfied, you can write this as 2.88 kilo Newton meter. Right? 2.88 kilo Newton meter. This is approach number 1 using the Flexure formula. This is approach number 2 using the calculus method. And we actually use the calculus method to finally reach this conclusion in the derivation. Right? All those guys who have seen the derivation now know that. Okay, rather can relate to that. There is one more approach, and that is a pretty much mechanics approach, engineering mechanics approach. I'll tell you, right? Just note these things down, take a screenshot and note it down. So guys, now let us start with approach 3, which involves a bit of engineering mechanics and a pinch of mathematics also. Now this is going to be super awesome. I've written something for you. Just try to read this. This F over here. Let me put it up in front of you. So there is this cross section. All the forces are inwards. All the forces are outwards. Under compression, under tension. There is going to be one single force which is going to represent all of these forces and which is going to be acting at a particular point. Right? The resultant of all of these forces because of this entire stress distribution is right here. Similarly, below the neutral axis, this region here, all the points are being pulled outwards. The resultant of all those outward forces is this fellow, and that also is acting at a certain point. We are yet to discover where that point is, but we can work it out, right? Using a basic principle of engineering mechanics, and to be very precise, we'll be using the concept of centroids, that too of a triangle. Now, this force is equal to the resultant force, obviously, either in compression or tension. In compression, the portion above neutral axis, tension below the portion. Volume contained by the stress distribution above or below NA. Now, some of you guys might be thinking, sir, how can this force be equal to the volume contained by the stress distribution? Well, my answer is to you would be to just believe in me for now. Believe in me right now. Let's work out the volume, and in the next 5 minutes, I'll clarify all your doubts, right? How that volume comes into the picture suddenly. Well, all of those doubts will be cleared. First of all, let us get the value of force. Listen to this. So you've got a triangle. You've got a triangle like this. This is base. This is height. How much is the area going to be? Half of base into height, isn't it? You pull this triangle outwards. There is going to be some volume swept. So you pull it outwards by a distance of, let's say, d. So let me just try to make it in 3D. In 3D, it would be something like this. This is very difficult to make. In 3D, it would be something like this. Let's say the triangle is right, something like this. If you push it backwards, then the triangle would be here, this way. Right? So this much area is half of base into height. Let's say this is A. When you multiply that A by this T, what you have is the total area. So A multiplied by T, so half of base multiplied by height multiplied by this distance. In the same manner, watch this. This over here is a right angle. So half of base is 20. Okay, so half of base is 20. Everything is in millimeters and newtons. So this is 20 Newton per mm square. Listen to this very quickly. Height is how much? 60 millimeters. That's 60 millimeters. And you have to stretch it. You have to run it through this distance. That is 60 millimeters. Okay, how much is this going to work out as? Just check. Let me make a quick check. This force is going to work out as, well, 2 and 2 will cancel out. 36, 1, 2, 3, 3 zeros. So, guys, the total force is going to be 36 followed by 3 zeros. This is in newtons. You can also convert this in 36 kilo Newton. There you go. 36 kilo Newtons. Okay. Just you need to keep on believing in me. Why I have done so. There is a very specific reason for that. Okay, let me now make some space so that we can get going. Right? One more step and then we'll be through. We'll again be getting the same value of internal moment as 2.88 kilo Newton meters. I need to rub this. So if you want to note something down, do note it or take a screenshot. So guys, let's move forward. Okay, the explanation time. Why I have written this formula? How come this force is equal to the volume of the stress distribution either above or below the neutral axis? Watch. Force. Here we don't have an average value of stress, but we can calculate that average value. You can clearly see that the stress is actually varying linearly. You see that the stress is 0 over here. It increases by some amount and it keeps on increasing until it hits a maximum value of 20 megapascals or 20 Newton per mm square. So how to work with such kind of stress which is linearly varying? What we can do is, we know at the neutral axis the stress is 0. So if you want the force, what you can do is you can find the average stress. That average stress can be multiplied with the area. This can be done very easily. Just take a look. What is the stress at this point? It's 0. What is the stress at this point? It is 20 megapascals or 20 Newton per meter square, per mm square. So you can write this 0 plus 20 divided by 2 and that is going to give you the average value of the bending stress at the cross section or the portion above the neutral axis, isn't it? And how much is this area? How much is only this area? We are talking about only this much area. So this is 60, this is 60. You simply multiply it with 60 and 60. Watch this now. Half. 0 plus 20, that is 20, 20. 60, 60. Into 60, into 60. This is exactly how this formula has been framed. I hope you can make the connect. Right? And again, if you try to solve this, what are you going to get? Well, the value of force which you will get is 36 kilonewton. Now, another important point. How far is this distance? I mean, this is really interesting. How high is this, or how much below is this force acting the neutral axis? This is very interesting, guys. And okay, now let me give you one more concept. It is based on the centroids of triangles, rather right angle triangles. Let's say this is B, this is H, then the centroid would be somewhere here at a height of H by 3 from the right angle. If the triangle is somewhat of this fashion, let's say this is B, this is H, then the centroid is right here again from the right angle. This distance is going to be H by 3 and this is the same concept which we'll be applying here, because in the side view you can see that there are two right angle triangles. Here is also we have right angle triangle and here. Okay, but how can this be applied and how can this help us find where the force is acting? Just watch. Super interesting, super amazing. So we've got a body, we've got a beam rather. Beam is somewhat this. Okay, so somewhere here we'll have the centroid. Just watch. How below? How much below? This is, guys, this is, you know very well, this is 60. Some time back I told you it is at a distance of H by 3. So 60 by 3 is going to be 20. Similarly, you've got a triangle here also, isn't it? So its centroid is going to be somewhere here. So obviously this is 60. So this is going to be again 20. What remains is this. This is 40 and this also is 40. This is a very basic approach, right? This also is 40 and let me finish this way. Okay, so all the forces, here we go. Everything in this region is compressive, so forces are here in this direction. Everything in this region is tensile, the forces is here. What is the value of force? It is 36 kilonewtons. The force are separated by some distance, and that distance, let me make that very clear to you. And if I can just pull it this way, the forces are acting exactly at this point. This entire arrangement of force is what is known as the couple, and what we are interested in is the moment of couple. Moment of couple, that is equal to the magnitude of the force itself, magnitude of force, and which in fact is multiplied by the distance between them. So if you watch carefully, the magnitude of force is how much? That is 36 kilonewtons. 36, okay, multiplied by the distance between them is 40 plus 40. This is 40 plus 40, that is going to be 80. So 36 multiplied by 80. Again, this has been worked out in kilonewtons. This has been written in millimeters. So the answer is going to be in kilonewton millimeter. Okay. So 30 multiplied by 8, 24, 240, and 6, 8, 48, 288, and a 0, 2880. That's the answer. And millimeters, so you've got a 10 raised to minus 3 over here. Strike it with this figure, and what you're going to get is 2.88 kilonewton meter. So this is exactly how you can work out the internal moment using 3 different approaches. Now my suggestion to all of you would be to remember this approach number 1, but again, you should know this test match approach also, this approach 2 that is using calculus, and this approach using a bit of mechanics and a bit of mensuration. That is why I told you mechanics plus math approach. Okay. Think about it. This is rather beautiful. Think about it. Right. So guys, that was all for today. I'm going to see you again in the next video. Until then, take care. Have a nice day. Keep learning. Keep watching. Thank you.